V to the field F, satisfying the three axioms. These three axioms are important. Here, f of u comma v is equal to f of v comma u, the bar, where the bar implies the complex conjugate of f of v comma u, and f of u comma u is always greater than equal to 0, and if f of u comma u is equal to 0, it implies u is equal to 0. If u equal to 0, converse is also true. If u is equal to 0, f of u comma u is equal to 0. And third property, f of alpha u plus beta v comma w is equal to, here alpha and beta are scalars belonging to the field F. Alpha into f of u comma w plus beta into f of v comma w. If these three conditions are satisfied for the function f from v cross v to f, then this vector space is called the inner product space. Here, from property 1, we can say that if f of u comma, if we take f of u comma u is equal to f of u comma u the whole bar, hence f of u comma u will always be real, and hence from P1 itself we can conclude that P2 is true. If the field is the real number R, then property 1 is nothing. For real numbers, conjugate will be the same. That is, f of u comma v is equal to f of v comma u. So in general, a vector space can be represented in several forms. It can be written within the parenthesis u comma v, or it can be written as u dot v. Some it will be notated as u comma v in this brackets. So in this fourth symbol will be used. Here, for example, let us take u is equal to a comma b and v is equal to c comma d, defined in C2 space. For example, we define u comma v as a into c bar plus b into d bar. That is, a into complex conjugate of first vector plus b into complex conjugate of second term. So if u comma v is defined as this, then we can say that it is an inner product on C. Let us see if it satisfies these three axioms. For f of u comma v is ac bar plus bd bar. F of v comma u is ca bar plus d b bar. By taking the whole conjugate f of v comma u, the whole conjugate, we get nothing but f of u comma v, that is ac bar plus bd bar. So first property is satisfied. Second property, f of u comma u, that is a, substituting in instead of v, we are substituting u itself. So instead of v, a bar plus b bar. A bar is nothing but modulus of a square plus modulus of b square. Since it is a square term, it will be always greater than or equal to 0. And the third property is also satisfied. It is just the distributive property. For some scalars, this property is also satisfied. Scalar multiplication and addition is also satisfied for this. Hence, this is a vector space. Sorry, it is an inner product space on the field C. It is usually referred to as the standard inner product. For this field, this example is usually referred as the standard inner product. Next, for second example, let V be the vector space over C of all continuous complex valued functions on the interval 0, 1. For f and g functions in vector space V, we define f, g by integral 0 to 1 f of t g of t bar dt. This is f of t comma g of t. We for g of t comma f of t will be given by integral 0 to 1 g of t into f of t bar. By taking the complex conjugate, we will get again f of u comma v, that is f of g comma sorry, f of t comma g of t. So first property is satisfied. Second property, we are substituting f of t in the place of g of t. Then we will get f of t into f of t the whole bar. It will be modulus of f of t square, and this vector by integrating this, it will be always greater than or equal to 0. And second property is also satisfied, and this holds. You can check for yourself. Third property is nothing but scalar multiplication. Scalar multiplication under the integral sign is distributive, and addition of the two vectors under this integral sign is also possible. Hence, all three properties are satisfied. Means we can say that V is an inner product space for this example, for this function. Next, a finite dimensional real inner product space is called the Euclidean space, while a finite dimensional complex inner product space is called the unitary space. Euclidean space is nothing but finite dimensional real inner product space. Hence, whenever we talk the square root of a real non-negative number, we shall always mean that positive value of the square root. This I will explain later in the upcoming pages. Okay, next, if x is a vector is a n tuple, that is vector in R power n, then its length or norm, we can define its norm or length by norm of x square is nothing but x comma x, which is nothing but summation of xi square, that is x1 square plus x2 square plus x3 square up to xn square will be nothing but norm of x square. Whereas if norm of x is taking the square this side, we will get square root of x1 square plus x2 square plus x3 square up to xn square for n tuple. For x and y in R power n, distance between x and y is defined as d of x comma y is nothing but distance between x and y. That is, norm of x minus y is given by square root of x comma y, x minus y comma x minus y in the inner product, which is nothing but summation square root of x1 minus y1 the whole square plus x2 minus y2 the whole square plus xn minus yn. Distance formula is nothing but norm of x minus y, which is given by square root of x1 minus x2 the whole x1 minus y1 the whole square plus x2 minus y2 the whole square plus etc. up to n. Then for u comma v in vector space V, norm u minus v is called the distance between u and v. Next, theorem statement. These 5 statements are important, which are useful in solving the problems. For inner product space, taking the scalars alpha and beta in the second terms, that is u comma alpha v plus beta w. Here, according to definition, we are taking f of alpha u plus beta v comma w, and this is also possible. F u comma alpha v plus beta w. If these scalars are taken in this second term, if we are taking out, it will be a complex conjugate. If it is real, it will be alpha. So if it is a complex number, it will be the conjugate. Alpha bar into u comma v plus beta bar into u comma w. Next, for alpha u plus beta v comma gamma w plus delta x given by alpha into gamma bar into u comma v plus alpha into delta bar of u comma x and beta into gamma bar of v comma w and beta into delta bar of v comma x. Nothing but simple multiplication and writing the inner products, vectors in the inner products. And 0 comma v is equal to, if 0 comma v is equal to u comma w, then it will be nothing but the 0 vector only. And if u comma v is equal to 0, then for every v, u will be 0. In other terms, if for every u, v will be 0. Then only we will get, if at least any one of the vector is 0, then it will be, the inner product space will be 0. And norm of alpha u is nothing but modulus of alpha into norm of u. These conditions are important in the inner product space. Next, Cauchy-Squarce inequality. This inequality is nothing but modulus of x comma y is less than or equal to norm x into norm y. When one is a scalar multiple of the other, then modulus of x comma y, inner product of modulus of x comma y will be equal to norm x norm y if y is a scalar multiple of x or x is a scalar multiple of y. Otherwise it will be less than or equal to sign only. Also we can see that every inner product space is a metric space. Now we see about orthogonal vectors, orthogonal set and orthogonal complement. Okay, what is orthogonal? Orthogonal is nothing but perpendicular. Perpendicular means any two vectors, means if they are perpendicular, its product will be 0, right? So a vector u comma v is said to be orthogonal if if its inner product is equal to 0. That is, if by definition it follows that u is orthogonal to v implies v is orthogonal to u. That is, if u comma v is equal to 0, then we can say that v comma u is also 0. Hence, if any of the conditions satisfies, then we can say that u is orthogonal to a vector v in the vector space, here inner product space v. And if w is a subspace of v, if W is the subspace of the vector space V, then the orthogonal complement of W. Here orthogonal complement we denote it by W perpendicular. Orthogonal complement of W is defined by set of all U in V such that U comma V is equal to 0 for every W. For every W, whichever U satisfies this condition, that will be in the set of, that will be the orthogonal complement set. For example, if u is a comma b and v is c comma d, we already know that u comma b defined by ac bar plus bd bar is an inner product. Then the vectors x equal to 3 comma 5 and y is equal to 5y comma minus 3i orthogonal, because inner product of x comma y is nothing but 3 into c bar. C bar is nothing but minus 5i plus 5 into d bar. D bar is plus 3i. So it will be minus 59 plus 59, which is equal to 0. X comma y is equal to 0. Hence, we can say that these vectors x and y are orthogonal to each other. Then for any subspace W, orthogonal complement of W is the subspace of V, such that W intersection W is nothing but the identity element. That is, only the intersection will consist only of 0. For any W intersection W complement will be nothing but the 0. The set will contain only 0 element. So orthogonal set. This is orthogonal vectors. Two vectors are said to be orthogonal if u comma v is equal to 0. For this, we can let us see an example. Here, once again. Here for a non-zero vector u, we have to find a non-zero vector u that is orthogonal to v1, v2 and v3. Here inner product space of in R3 is defined by inner product u dot v1. Here we have I have represented as u dot v1 for any vector u in u. For let us assume u is equal to a comma b, and we know we should find u. Here orthogonal condition u dot v1 should be 0. U dot v1 is defined by multiplying the corresponding positions. That is 1 into a, 1 into a, 1 into b plus 2 into c. A plus b plus 2c equal to 0. And we have for v2, u dot v2 equal to 0 implies 2a plus b plus 3c is equal to 0. And u dot v3 equal to 0 implies a plus 2b plus 3c equal to 0. I'm writing in this matrix form, and 1, 1, 2, 2, 1, 3, 1, 2, 3, which is similar to, I'm reducing it to row reduced echelon form, and I will get 1, 1, 2, and R2 minus 2R1, I'll get this row. R3 minus R1, I'll get this. From this, I can say B plus C is equal to 0. That is B equal to minus C. And from the first vector, I can say A minus C plus 2C equal to 0. Since we already know here, instead of B, I'm substituting it as minus C. Hence, we can say that A is equal to minus C. So, for a value, if we take A is equal to 1, B will be, C will be minus 1 and B will be minus of minus 1, which is plus 1. So, here the vector U is orthogonal to all these three vectors. So, in order to find the vector U, we have taken these conditions. Since the orthogonal definition is U dot V is equal to 0. U dot V is equal to 0. That is inner product of U comma V is equal to 0. See. Next, orthogonal set. Orthogonal set. A subset X of V is said to be an orthogonal set if for any X and Y, X comma Y equal to 0. Whenever X naught is equal to Y. So, set of here a subset of X. So, we are taking a subset of X of V such that for any X and Y, whichever vectors X and Y in X satisfies these properties, it will be in the set X. So, that will be called as an orthogonal set. If this is the vector space V, then here this is the subset X. Here, if we take any two vectors, it will be orthogonal to each other for any two non-equal vectors. That is X equal to not Y. If we take any two vector, it will be orthogonal to each other. Then this subset is called the orthogonal set. This subset Orthonormal set. This subset X of V is called orthonormal if it satisfies two conditions. Then it should be an orthogonal set. That is, X. If we take any X and Y, its inner product must be 0. And norm of if its norm is equal to 1, then we can say it is an orthonormal set. So, if a orthonormal set is nothing but an orthogonal set with the first condition. So, existence of an orthonormal set. Every inner product space V which is not equal to 0 possesses an orthonormal set. So, if it is a non-zero vector space, that is inner product space, then we can say that it has an orthonormal set. For example, for alpha not equal to 0 in V, norm of alpha is not equal to 0. Then alpha by norm A containing only one vector is necessary, and this vector is itself a orthonormal set. For we are taking this as U comma U is nothing but 1 by norm A of alpha comma A by alpha. Now I am taking this norm A or norm alpha also outside. Then 1 by norm alpha square is norm alpha square, and alpha comma alpha is nothing but norm alpha square, which is equal to 1. So, norm X is equal to 1. Norm of X is equal to 1. This property is satisfies, and for here this is equal, so we no need to check the second property. So, for every inner product space and which is not equal to 0 possesses an orthonormal set. Complete orthonormal set. A maximum orthonormal set of vectors in an inner product space V is called a complete orthonormal set. That is, if it contains maximum number of vectors, then it will be called as a complete orthonormal set. An orthonormal subset M of V is a complete orthonormal set if for V in V, V in a vector space V, if V is orthogonal to M, implies V is equal to 0. That is, no non-zero vector in V is orthogonal to M. Then it will be called the complete orthonormal set. Next, this definition, this theorem, this is an important theorem. Here, if V is an n-dimensional inner product space, then there exists complete orthonormal set in V, and every complete orthonormal set has n elements. The orthogonal dimension of V is same as its linear dimension. Next, orthonormal basis. Here, a basis of an inner product space consists of mutually orthogonal unit vectors. That is, U1 if orthonormal basis means if x1, x2, x3 are the orthonormal vectors. Example, x1, x2, x3 are the orthonormal vectors, then x1 and x2 are orthogonal, x2 and x3 are orthogonal, and x3 and x1 are orthogonal, and these this will be called as the orthonormal basis. That is, these unit vectors, basis of an inner product space, consist of mutually orthogonal unit vectors, which is called the orthonormal basis. Gram-Schmidt orthonormalization. That is, this is an important theorem. If x1, x2, xn are linearly independent set of vectors in a vector space V, then there exists an orthonormal set of vectors. Let us consider the orthonormal set of vectors as y1, y2 up to yn. Orthonormal set means x in for here orthonormal set implies norm of x is equal to 1, and for x comma y is equal to 0 for every x and y in x. Here y comma y for y1 into y2 is equal to 0, and norm of y1 is always 1 for every y. Then the Gram-Schmidt orthonormalization nothing but if this is a linearly independent set of vectors, and there exists an orthonormal set of vectors which are equal, that is x1, y1, whose inner product space will be always equal. x1, x2, xi is equal to y1, y2, yi. For every I, it will be equal. Here, let us take the example. First, I'll tell the example in this case. Here, A is equal to 1, 2, 3, 6. We have to find P inverse AP. Here, P is nothing but the we have already seen P is nothing but the linearly independent vectors that forms the matrix. That is, eigenvectors which are linearly independent forms the matrix P. Here P is any matrix. We have to find P, and then we have to find P inverse AP. First of all, we find the eigenvalues. A minus lambda is equal to 0, and lambda square minus 7 lambda plus 6 minus 6 is equal to 0. That is, lambda is equal to 0, 7. For lambda is equal to 0, we find the eigenvector Ax equal to lambda x. So by substituting lambda equal to 0 here, we get Ax equal to 0. That is 0, 0. Here x plus 2y is equal to 0, which implies x equal to minus 2y. I am putting 1, and as for I am taking y equal to 1, and x will be minus 2. And for lambda equal to 7, Ax equal to 7x, 7ix. Here a minus 7 is nothing but instead of lambda I am putting 7, so minus 6, 2, 3, minus 1. That is minus 6 plus 2y is equal to 0, which implies y is equal to 3x. If I take x equal to 1, I'll get y is equal to 3. Here I am finding the unit normal vector. That is, E1 will be nothing but x1 by norm of x1. So x1 is minus 2, 1. Here norm x1 is which is nothing but square root of, this is a vector 2 minus 2 comma 1. So square root of x1 square is minus 2, the whole square is 4, plus 1 square is 1, which is nothing but root 5. So E1 will be minus 2 by root 5 and 1 by root 5. Let us take this norm. X2 is equal to, by taking norm, root of 1 plus 3 square 9, which will be 10. X2 will be 1 by root 10, 3 by root 10. We have found out E is equal. This is E and this is X. So we are finding F2. F2 is defined by X2 minus inner product space of X2 comma E1 into E1. So X2 is nothing but 1 by root 10 by 3 by root 10, and X2 inner product of X2 into E1, that is 1 into 1 by root 5 root 10. I'm taking multiplied is common, that is minus 2. 1 into 3 is 3. Minus 2 into 1 is minus 2 plus 3. Minus 2 plus 3 into E1. E1 is nothing but minus 2 by root 5. Here in this we can take 1 by 3 also common. In order to ease, I have found the unit I have divided by its norm. So I am taking 1 by root 10 outside. It will be 1 by 1, 3 minus 1 by root 5. 3 minus 2 is 1. 1 by root 5 minus 2 by root 5, 1 by root 5. I am multiplying root 5 minus 1 by root 5 inside. So plus 2 by 5 minus 1 by 5. So it will be 7 by 5 root 10, 14 by 5 root 10. So norm of F2 is nothing but root of 7 square by 5 square into 10 plus 14 square by 5 square 10. I am taking 5 square 10 outside, which will be 5 root 10. Square root of 7 square 49, 14 square is 196, which is nothing but root of 245. 245 is nothing but 49 into 5. So I'm taking 49 outside, that is 7 square outside. So 7 root 5 by 5 root 10. So I am finding E2. E2 is nothing but F2 by norm F2. So F2 is nothing but 7 by 5 root 10 into norm F2 is 5 root 10 by divided by norm F2, which is nothing but into 5 root 10 by 7 root 5. Upon cancelling, we'll get 1 by root 5 into 2 by root 5. So P will be nothing but, here these two vectors are mutually independent, and also these are unit normal vectors. So minus 2 by root 5, E1 I'm writing it as E1 is nothing but minus 2 by root 5, 1 by root 5, minus 2 by root 5, 1 by root 5. E2 is 1 by root 5, 2 by root 5. So this is P. P transpose P is equal to identity. So P transpose is the inverse element. P inverse exists, that P inverse is nothing but P transpose. And P inverse AP is multiplying these all three vectors. I'm taking root 5 and root 5 outside. So multiplying all these matrices, I'll get 0, 0, 0, 5, 0, 35, and which is nothing but 0, 0, 1, 7. P inverse AP is nothing but 0, 1, 0, 7. Here we are applying the same process for these three vectors. That is beta 1, beta 2, beta 3. Here, there we have taken eigenvectors. Here they have given beta 1, beta 2, and beta 3. They are asking us to apply the Gram-Schmidt process to find the orthonormal basis. We have to find the orthonormal basis with the standard inner product. Let us assume alpha 1 is equal to beta by norm beta 1. Norm beta 1 is nothing but square root of 1 plus 1, which is nothing but root 2, 1 by root 2 into 101. Beta is nothing but 101, which is nothing but 1 by root 2, 0, 1 by root 2. Now gamma 2, let us assume gamma 2 is equal to, gamma 2 is given by, gamma 2 is equal to beta 2 minus inner product of beta 2 into alpha 1 into alpha 1. If for gamma 3 will be beta 3 minus beta 3 alpha 2 into alpha 2 minus beta minus beta 3 comma alpha 1 into alpha 1. For gamma n, if here they have given three vectors, if there are n tuples, so gamma n will be beta n minus beta n into alpha 2 into alpha n minus 1 and n minus 2 up to so on. So for gamma 2, it is beta 2 minus inner product of beta 2 into alpha 1 into alpha 1. So beta 2 into inner product of beta 2 into alpha 1. Beta 2 into alpha 1. Alpha 1 is this. Beta 2 is 1, 0 minus 1. So multiplying this 1 into 1 by root 2. 1 into 1 by root 2 plus 0 into 0 minus 1 into 1 by root 2. Corresponding elements we are multiplying corresponding, that is dot product. We are taking the dot product. So which is equal to 1 by root 2 minus 1 by root 2 is nothing but 0. So beta 2 comma alpha 1 is a 0. So gamma 2 is nothing but 1. Beta 2 is 1, 0 minus 1 minus 0. That is 1, 0 minus 1. Norm of gamma 2 is square root of 1 plus 1, 2. So alpha 2 will be gamma 2 by norm of gamma 2. We have to find alpha 1, alpha 2 and alpha 3. Alpha 1 is nothing but given beta 1 by its norm. Alpha 2 is nothing but we have to find some gamma with by Gram-Schmidt orthonormalization process that should be orthogonal. So gamma 2 we have found out by this formula, and we are taking the norm. So alpha 2 is nothing but gamma 2 by gamma 2 square, which is nothing but norm of gamma 2, which is nothing but 1 by root 2 into 1, 0 minus 1. So this is alpha 2. Now we are going to find out gamma 3. Gamma 3 is given by this formula. Gamma 3 is nothing but beta 3 minus beta 3 comma alpha 1, inner product of beta 3 comma alpha 1 into alpha 1 minus beta 3 comma alpha 2 into alpha 2. We are finding the inner product of beta 3 and alpha 1. So beta 3 and alpha 1 will be 0 into 1 by root 2 and 3 into 0 plus 4 into 1 by root 2. 4 by root 2. It will 4 into 1 by root 2, which is nothing but we can say it is 2 root 2. For 2 into root 2 into root 2, we can write 4 as 2 into root 2 into root 2. By cancelling and root 2 and root 2, we will get 2 root 2. Beta 3 into alpha 2. Here beta 3 into alpha 2. Alpha 2 is nothing but this one. So 0 into 1 by root 2, 3 into 0, 4 into minus 1 by root 2, which is nothing but minus 2 root 2. Now we are finding gamma 3. Gamma 3 is beta 3, 0, 3, 4 minus its inner product is 2 root 2 into alpha 1. Alpha 1 is 1 by root 2, 0, 1 by root 2. And inner product of beta 3 minus alpha 2 is minus 2 root 2. So it will become plus 2 root 2 into 1 by root 2 comma minus 1 by root 2, which is nothing but 0, 3, 4 minus 2, 0, 2 plus 2, 0 minus 2, which is nothing but 0, 3, 0. Gamma 3 is 0, 3, 0. Norm of gamma 3 is nothing but square root of 9, which is nothing but 3. So alpha 3 is 0, 1, 0. Hence alpha 1, alpha 2, alpha 3 is 1 by root 2, 0, 1 by root 2, 1 by root 2, 0 minus 1 by root 2, 0, 1, 0. This will form the orthonormal basis of V3. That is, we are taking this as alpha 1. Alpha 1 is nothing but B1 by norm B1. So we are finding some gamma 2 using this formula and taking its norm. We are dividing gamma 2 by norm gamma 2. That will be alpha. And gamma 3 is given by this formula. By taking, we are finding the gamma 3 and dividing its by norm, we will get alpha 3. These three vectors will form the orthonormal basis. Now we are applying the Gram-Schmidt orthonormalization to the orthonormalization process to the vectors x1, x2 and x3 like in this form. Here I am taking y1. I am assuming y1 and y2, y3 are form the orthonormal basis. So y1 will be nothing but x1 by norm x1. 1 by norm x1 into x1 is given here. Norm x1 is nothing but square root of 2 square plus 1 square plus 2 square, which is nothing but root 9, which is nothing but 3. So y1 will be 1 by 3 into 2, 1 root 2. Next, I'm going to find u2. u2 is given by this formula, that is x2 minus inner product of x2 comma y1 into y1, which is given as x2 minus inner product of x2 comma y1 can be defined by y1 transpose into x2, that is y1 into x2. 4 into 2, 4 into 2 is 8. Y1 transpose is nothing but 4 into 2 is 8, plus 1 into 1 is 1. 8 plus 1, 9. 9 by 3 is nothing but 3. That is 1 by 3. Here x2 is 410 minus inner product of x2 comma y1 is 1 by 3 into these two vectors. So 9 will become 9. This value is nothing but 9. And y1 is 1 by 3 into 212. So 9 by 3 into 3, it will get cancelled. So 410 minus 212, which is nothing but 20 minus 2. We are taking the norm of this u2. U2 norm is 2. Norm of u2 is nothing but square root of 4 plus 4, which is 8. 8 can be written as 2 root 2. So 1 by 2 root 2 into 20 minus 2. That is y2 is 1 by root 2 into 10 minus 1. Next we are finding u3. u3 is nothing but x3 minus x3 into y1 into y1 minus x3 into x3 comma y2 into y2. Now x3 is 3, 1 minus 1. Inner product of x3 comma y1 is taking this transpose. Taking the transpose, we'll get 3 into 2 is 6. 6 plus 1 into 1 is 1. 6 plus 1 plus 2 into minus 1 is minus 2 divided by 3. 7 minus 2, 5. 5 by 3. It will be 5 by 3. So 5 by 3. Here instead of x1 we are substituting, and inner product of x3 comma y1 is 5 by 3. Y1 is nothing but 1 by 3 into 212, which becomes as 5 by 9 into 212. And x2 comma y3 is nothing but x3 comma y2. Y2 is 10 minus 1. 10. X3 is 10 minus 1. 1 by root 2 into 10 minus 1. 3 plus 0 plus 1. That is 4 by root 2. 4 by root 2 into root 2, it will become 2. 4 by root 2 in 4 by 2 is 2. And y2 is 101. By substituting, we will get minus 1 by 9, 4 by 9, and minus 1 by 9. Taking the norm of u3, norm of u3 is nothing but 3 root 2. By substituting this, we will get y3 as 1 by 3 root 2 into minus 1, 4 minus 1, which is nothing but here y1, y2, and this y3 forms the orthonormal basis. Next, if norm of x plus y is equal to norm x plus norm y, then we have to prove that x and y are linearly dependent. So given x plus y is equal to x plus y, then squaring both sides will get norm of x plus y square is equal to norm x square plus norm y square plus 2 into norm x norm y. We know that norm of x square is nothing but inner product of x comma x, that is norm of x plus y the whole square is equal to inner product of x plus y comma x plus y. So x square plus y square plus xy plus yx is equal to inner product. We are substituting the inner product, which is equal to x square plus y square plus 2 norm xy. So cancelling x square and x square plus y square, we'll get xy plus yx, which can be written as 2 real of x comma y, since we know that x comma y is equal to y comma x, the conjugate. So 2 times real part of x comma y is nothing but 2 times norm x norm y. So norm x, norm y is nothing but real part of x comma y, which is less than or equal to modulus of norm xy. Since real part of z is less than modulus of modulus of z, we can write x comma y is less than or equal to a real part of x comma y, which is less than or equal to modulus of x comma y. So also by Cauchy's cross inequality, we have x comma y is less than or equal to x norm x norm y. That is, we are writing like this: norm x norm y is greater than or equal to modulus of x comma y. From 1 and 2, we obtain x comma y is equal modulus of x comma y is equal to norm x norm y. So Cauchy's cross inequality holds, then x and y are linearly independent. See, if these are equal only if y is a scalar multiple of x or x is scalar multiple of y. Hence, it is linearly dependent. Sorry, linearly dependent. It's consider complex C square with standard inner product space. Then we have to show E1 and E2 is the orthonormal subset. Here E1 and E2 is nothing but the standard orthonormal vectors, standard vectors 1, 0 and 0, 1. And we have to show that this is a subset, orthonormal subset of C2. Since E1 comma E1 is nothing but AC bar plus BD bar. AC bar E1 comma E1 is nothing but 1, and E2 comma E2 is also 1. We get a norm of E1 and norm of E2 is equal to 1. So first condition is satisfied. For orthonormal, if it should be an if it is a subset is called an orthonormal subset if its vectors norm is 1 and any two vectors in the subset inner product should be 0. Hence E1 first condition is satisfied here, and second condition E1 comma E2, that is AC bar 1 into C bar 0 plus 0 B D bar 0 into D bar, which is equal to 0. Hence E1 comma E2 forms the orthonormal subset of C2. For C3, it will be E1, E2, E3, 1, 0, 0, 0, 1, 0, 0, 0, 0. This forms the standard orthonormal subsets. Next, orthogonal transformation. Orthogonal transformation. Let V be an inner product space. Then a linear transformation is said to be orthogonal if Tx comma Ty is equal to x comma y. Inner product of Tx comma Ty is equal to inner product of x comma y for all x and v. Then we can say that the linear transformation is orthogonal. Next, if let T be a linear transformation, then we can say that T is orthogonal. If T is orthogonal, Tx, that is norm x, Tx equal to norm x for all x in V. And all these conditions are mutually equivalent. The T takes an, if T is orthogonal, T takes an orthonormal basis to an orthonormal basis. That is, T is a vector from V to V. Here, all the orthonormal